as I used to, so I will make even more mistakes, I'm afraid. So please pay attention. If you don't understand something, then that means I am making mistakes, or I change the language and I'm speaking in Russian or try to speak. And so please always correct me, because there will be a chaos if you will not pay attention and correct me. To speed up my lecturing, I try to summarize where we are at the moment. So we consider this equation here. This is our basic equation, linear SPD, second order. L is this second order operator, M is this first order operator. So the kind of equation which appears in filtering theory, plus three terms F and G, and here multi-valued Wiener process, and that means summation with respect to the coordinates. So the operators, we have D1 many operators. Also G is a vector valued process, so with coordinates rho. This has also coordinates rho and the summation. We have an initial condition U0, and I repeated here our basic conditions on the equation. So the first condition, assumption 1, is that the coefficients have continuous derivatives in x up to order m, and the function, the coefficients and the derivatives are bounded in magnitude by a constant c. Right? I also introduced, I don't know whether I wrote the 2 here last time or did not, but that doesn't make much difference. So the initial condition, m norm squared expectation, plus this quantity from the free terms is denoted by this kmt. M stands for the integer which is fixed at this moment, any non-negative integer, which appears here in condition A1 and also in condition A2. Condition A3 is the stochastic parabolicity, so the strong version. So kappa here is a fixed constant, fixed positive constant, and this is the condition concerning the coefficients, not all the coefficients. Maybe I never stressed that or emphasized that here only from 1 to d should be considered the indices. Generally here alpha beta means indices from 0 to d, right? And the zero index means that that the corresponding derivative is not a derivative, but the identity operator, just to have a short writing. So once again, we consider the equation in the whole space Rd. So t in t on a finite interval, in x on the whole space. I also sometimes may use this notation, ht, for the product of these two. Alright, so always we assume that m is greater than d half, d is the dimension. And first, let's say, before even assuming this assumption, we know from the general theory that there exists a solution, so-called generalized solution, which is a continuous L2 valued stochastic process, satisfies the equation in the weak sense. But it turns out, because the coefficients and the free terms are as regular as the A1, A2 assume, therefore, in fact, we have about this process or a modification of it, and therefore we may assume that it is HM2 valued and continuous process, and also, that's important to know that in this case, also it is in the HM+1 space. This boldface H is the notation used by Professor Kurov, so you remember that that means one considers the m plus 1 norm, Hm plus 1 norm in X, square of it, integrate over the time interval, and that is finite. So this is the other property. Now we assume that m is greater than the dimension half. Then, because of Sobolev embedding of Wm2 functions into continuous bounded and continuous functions, we can easily see that in fact this solution has a continuous in Tx modification, and we always, when it is possible to have more regular version, because of our assumptions, we always consider more regular version. So from now on, we always consider that our solution, this solution is continuous in T and X. Right, now the approximation, the finite difference scheme here is defined by replacing the derivatives by finite differences. So this is how LH is defined, that instead of the d beta this type of finite difference, so it plays a role that here it is minus h. So in the other direction, then if I take h, so this is an obvious and easy to remember, I think, and also the mh is defined by substituting the derivation here by the finite difference. Obviously, when alpha is 0, then the corresponding finite difference, so the zero index is defined as the identity, again, in order to have a short writing. Yes, so defined. Okay, and then how we view this equation, which so the scheme, that we consider it the natural way to consider it on the grid. So this is the GH, so a lattice with mesh H, and we consider it on this because this notation, right, that when I write delta HI, that means finite difference in the i's basis direction, so therefore the corresponding lattice is like this. Then first we use on this lattice the L2 norm of functions which are defined on the lattice, and this is the definition of this discrete L2 norm, which I denote simply by little l2, which is just little l2 but also multiplied by h to the d in order to have the discrete L2. And we have seen that lemma that once m is greater than d half, then the function, we consider its continuous version, on the lattice is in L2. So there is an embedding of these into L2. So because of this, we can consider the free terms f and g, and also the initial condition u0 restricted onto the lattice, first because of continuity, and second that we can from this know that the free terms are little l2 valued functions, right? And because, have I written that? Oh, here, right. Again from this, from a lemma, so this lemma here, we know that if we consider ftx on the lattice, So that is an infinite vector now, also G, each component. Then these are L2 valued processes, and moreover, this estimate holds because of the lemma, the FT-L2 norm, little L2 norm, is estimated by a fixed constant, and the WM norm or HM norm of the function, so order of F and of G, and therefore I could have also written here that U naught squared on L2 plus, and then we have this estimate. Right? And then we can use Ito's theorem, that is a Hilbert space valued theorem, that if we have an SDE and a Hilbert space, I will formulate it again more precisely later, such that the, let's say, linear and the free and so if this is satisfied, then there exists a unique H-valued, so here H is the L2 valued solution, and moreover, it is continuous in L2, and moreover we have an estimate as well. So once again, this is a classical result, but in an L2 setting or in a Hilbert space setting, not a difficult stuff at all. And so our aim is to estimate the difference of the true solution and the solution of the finite difference scheme in this norm. So supremum over the grid, supremum over the time, expectation at the second moment of it, and also the L2 norm second moment, supremum uniformly in time. So this is the error which we would like to estimate. Yes, I think I have told nearly everything. No, one more thing, important thing here, that okay, this is the natural approach, but the other point of view, which is technically advantageous, that we consider the equation, the finite difference scheme, now not on the grid, but instead of that we consider in the whole space, because it is well defined also in the whole space. So again, then we know by Ito's theorem, Hilbert space valued version, that there exists a continuous L2 valued solution. This is what now I try to keep the notation correct. This is what we use U bar H in order to make the distinction between the little L2 solution and the capital L2 solutions, right? Because at this moment we don't know that these are the same. In fact, it turns out that these are the same if M is greater than V hat, but okay, this time we just write it like this. And instead of considering then this difference and estimating, we consider, where have I written down? Here. We consider this. And this is what I denote by VH. So the capital L2 solution of the scheme minus the true solution, and that is what we want to estimate first, and from here we relatively easily obtain an estimate for this. Right? So let us write down an equation for VH. It's easy. We take the difference, the equations, and then we got what is written down. We have seen this before, and the free term now, it is considered now as a free term, is FH is defined here and GH defined here. So the approach is the simple approach from numerical analysis, that from this equation we estimate the solution VH by in terms of the initial condition, which is 0. Initial condition is 0, so that is not used, but in terms of the free terms FTH and GTH. In order to get a good estimate, and this is the essential part of the whole story, we should consider these types of equations and produce the necessary estimate. And this is why I have written down, and that was theorem 2, but I haven't had more space here, so I write it down. What is the basic, let's say, theorem which gives the estimate? So I repeat this. I repeat what was already done last time, or the formulation was given. So this is theorem 2. So we consider F. I should first assume A1 and consider F beta processes from A and also G row processes from this H and M2. So assume and consider that, and with this equation du, again I used here the u, but nothing to do with that one. This is separate auxiliary theorem. So du equals LH u. Maybe I write it in the, that is even better. Write it in the form delta minus H beta A alpha beta delta H alpha UH plus the F beta, so beta is running from 0 to D, oops, I want it not here but here, and dt plus the B alpha delta alpha UH plus G dWt with an initial condition, let's say UH 0 equals the same U naught. Then this equation, so first statement, that this equation admits a unique continuous L2 valued solution, and moreover UH is continuous HM valued and also it is, oh no, that I will not say. Sorry, that's it. It continues and HM valued. And the second, that assume also the stochastic parabolicity condition, then we can estimate independently of H the solution, and the estimate is the following. Then the supremum in time of UH M norm squared expectation plus the expectation integral from 0 to t, sum over I from 1 to d, the delta hi acting on UH M norm squared, so this is the integral norm, dt is less than or equal than a constant n times the expectation of the u naught squared m norm plus integral from 0 to t, and the sum, or let me just use always that if we have a vector like the f, the beta are the indices, so a vector, then I just use the letter f for the vector, and when I write f m norm squared, that means each component is taken, and Wm2 norm squared is considered and summed up, right? So the vector version of the Sobolev norm, plus similarly for the G dt, and always I use for the constant n, and that when we will calculate and estimate things, and n is a constant which depends only, I have written down here, when I write an n that can be different in the same line, but always a constant which depends on the constants involved, right? The c, the kappa, ellipticity or strong parabolicity constant, dimension, the m, the regularity of the data, and also on capital T. So the constant means always this one. Okay, so now we are going to prove this.
You missed some expectations.
I missed an expectation here, thank you. That's not so bad that only now I start making mistakes. I usually start already in the first sentence. Okay, so we are going to prove this. I get rid of the other stuff. Okay, so the first, in fact, we have already seen this one. The first sentence, the first statement is already proved, or I told, but just in case, let us make it clear what we use here. So because it wasn't very clear, I'm afraid, last time. So the first sentence uses Ito's theorem, a simple Hilbert space valued Ito theorem. So let me formulate a version which is true, that we consider a linear SDE, but in Hilbert space. So dxt here AT operator acting on xt plus nf t dt plus bt xt plus gt dwt. So just for simplicity, finite dimensional. And so this row is running from 1 to d1, and x naught is in Hilbert space, let's say separable Hilbert space measurable. Oops, yeah.
There must be some term over h in the statement of your result.
Sorry, where?
No. Yes. There must be some h on the right hand side.
Independent weights.
In the right hand side, here you want to have an h or what?
Yeah.
No, nothing. No h at the moment appearing in the estimate. Yes, there is no. But the important thing what I mentioned, and maybe it wasn't clear, that the n is independent of h. So this is why I mentioned that the constant n, whenever I am using a constant n, the dependence can be only this one, no dependence on it. I'm not so sure again I answered the question.
When we have a difference that there is h of it.
Oops. Can I? Okay, so if we have that the AT is a linear operator, let's say from the Hilbert space, now this capital H is a separable Hilbert space, oops, sorry, into H, bounded, its norm, let's say, is bounded by a constant C for all t and omega, for almost every omega, no. But important, the similar for the operators, operator norms that bounded by C, and the Ft and Gt are h-valued measurable adapted, so adapted h-valued processes such that the integral from 0 to t, the ft squared dt is finite almost surely, and in fact it is enough to have just the f factor, right, then not the square, but for us it's good enough that the square. Here the h norm is finite almost surely, and moreover x naught is f naught measurable and it is in h. Under this condition there exists a unique continuous h-valued process which solves that valued solution. As already it was discussed, I think, today, maybe by both lecturers in the morning, that this can be viewed in two ways. The same, either as the meaning of the solution. Two ways, either just directly without using test functions, which means little elements, not little h, but elements from h, or by using test functions. These are the same. So, okay, the proof is exactly the same as in the finite dimensional case. So we know this theorem, and by this theorem, then we have, first of all, when we consider h as the capital L2, then we got a capital L2 valued continuous solution, unique. Then we consider the case, so apply now this with H equals L2 and then H equals capital L2 and correspondingly with the what capital L2, twice I have written that down, sorry, WM2, yes, then it is just a simple checking that the operator what we have here is satisfying these conditions in that case. So therefore we can get the HM valued solution, and because of the uniqueness we have that extra regularity, that the L2 valued solution is also an HM valued solution. Alright, so the first thing is an easy thing to check. The harder is the second, though it is very, very similar to get this estimate. It's very, very similar to that how in the variational approach the similar estimates are obtained, but in this setting. So let us see the proof of the second. But before proving it, let us use a lemma which captures the essential part of the estimate. So let us denote by QT and phi this kind of quadratic form that twice phi LH phi plus sum over rho, which is from 1 to d, the MH, this depends on t, MH d phi squared. This expression, I think this is the one which I want. Yes, when I write this, that means the inner product in L2. Maybe I put a 0 to emphasize this is inner product in L2. This is the norm in L2, and this let us consider this for smooth functions phi. Just first for that in. Okay, that's that one. Right. And then what we claim is that y for smooth. Let us already for L2 this, and we claim that it is less than or equal than kappa with minus, and I use the summation from 1 to d delta hi phi and m norm plus why I don't use okay, that's fine, plus n times oops, I wanted in yeah, okay, n times phi m. So this holds for every phi from L2 this estimate, where the n, as always, depends only in this case on c, kappa, dimension, and m. Time is not involved. So this is true for all t. Sorry?
Squared, no?
And squared, yes, thank you. Okay, Now the proof. So let us consider first the case m equals 0, and then estimate first that part. So that is 2, or without 2, okay, 2 phi, and here the delta minus h beta a alpha beta delta h alpha 1 phi, as this is what we want first to estimate, right? So this is the L2 inner product. We take the adjoint of this delta in the L2. We drop onto phi or phi, then twice delta minus h beta star on phi a alpha beta delta h alpha phi. So far seems okay, and notice, and this is important, that like with the derivatives, we have the same thing with the finite differences. So the analogous thing, that the delta star minus h I or j equals the minus delta h j when j is 1, 2, and so on. So when we have not the identity, because the adjoint of the identity operator is itself the identity. So this is an easy exercise to check. So therefore here what we have is so this one equals the minus 2 delta h j phi and a. Let me write the case when I take out the alpha. For the alpha I do not consider first the 0, so I write here I and then j delta h I phi. This is the main term I need. Then minus 2, still I keep the delta hj phi, and I consider the case when when alpha here equals 0, so then I have a 0 j and the identity, so that is fine. And okay, then I consider now the case when the beta equals 0. So in that case we have this positive 2, the phi, and a alpha 0, right, and alpha, and then so I wanted that's one, delta h alpha phi, right? So I have written down, I hope, properly. And okay, this is less than or equal than the minus 2, and here maybe I write in the integral form. This is the integral here aij, and then the delta h I phi times delta, oh this is delta h, not minus, j phi dx. Yes, the first part. And why I wrote here less than or equal, because this part is estimated easily from above by taking just the absolute value, using Cauchy-Bunyakovsky and the Young inequality, when you know that when you have a product AB, absolute value, you can always take any small positive number epsilon times A squared plus an n, depending on only the epsilon, be basic simple estimating in this field. So using these two after the after the Cauchy-Bunyakovsky in L2, we can have this, that for sufficiently small epsilon times the delta h I norm in L2 summing up. Yes, when I wrote this, we have always summation, you know. When I write I and j as indices, that means that the 0 is not taken by them. They run from 1 to d. Right? Okay. So here we have that summation from 1 to d. And plus, then we get the constant times the L2 norm squared of phi. So this is our basic estimate for the so maybe we just remember that I write it down here. Just I take that this part is less than or equal, then a small, this important part, right? So I continue, I go up here, continue writing here. I estimate this also because by the, oh no, not yet, what I'm doing, not yet. I should keep this one, so maybe I just write that part as J1, that term, so this is for me now J1, so J1 plus the epsilon times I from 1 to d, delta h I squared plus n phi 0 squared. Yes, but good to remember that we have here such a quadratic form below the integral, and you notice, yes, this is how you can remember that is here the aim, that to use the parabolicity condition. So this is a term already from there when the z plays the coordinates, this one. Okay, so we have this estimate, and now for the m, yes, capital M. So for that part, let us write that is the delta h alpha times here the b alpha and rho phi, and that squared, also summation with respect to the rho I will write or specify. So what is that? We separate those where which is the non-zero. So when alpha is taking values 1 until d plus the term when alpha equals 0, and we square it, right? First we write that one. So what do we get? We get that then that bi rho, bj rho, and the delta h I phi multiplied by the delta h j phi. And so this one, right, okay, and then okay, let us not take any absolute value at the moment. There's this one here, and plus then twice, where when we have the term, the mixed product with the zero indices index and the non-zero indices, so that means twice the bi rho delta and h I phi, and that is maybe I should write it like this, that here I consider the L2 norm, and here then I have the integral, and this one is multiplied by the b0 rho and just phi. So this we get twice, and plus when we take the square of the term with index 0, so that means b0 rho squared, where put the square, and times phi squared. So this is integrated, so the dx, and then this is less than or equal. Then let us denote this part by I2. So I2 plus, and then just before we do the same estimate using the boundedness, that I forgot to say, obviously. One should also use the boundedness of the coefficients here, and then by Cauchy-Bunyakovsky first, and then separating with small epsilon the one which has the delta, the finite difference, so epsilon times again, and then summation over, oops, maybe I also, oh no, this time I don't, from 1 to d, delta h I phi, and 0, okay, and then plus, so this is the I2, and plus n times the phi squared 0. Here we also have the summation with respect to rho. Here I do not write summation, thus repeated indices in the summation convention means, short way, that there is a summation here with respect to rho. Also here summation, so everything is right, except here I should write summation with respect to rho, and so we got that. And then the final step, I write it now here, okay.
You don't want to put the dependence of epsilon on the other end.
You want me to write this, right? Okay, that's fine. And now for the Q5, then we have the estimate that this is less than or equal than I1 plus I2 plus the small epsilon or even twice if that is the same sum from to d delta hi phi squared plus the m times phi squared 0, and the important thing is that the I1 plus I2 is, yes, we already forgot what was the I, but okay, we have that 2, and so you can check that we get the following, that 2 aij minus then the 1/2. Here you see the same terms which we had at aij, but I took out the 2 here, and therefore I take the 1/2 bi rho bj rho. Oops, probably it is not readable. Let me write it once again. So integral twice aij minus 1/2 bi rho bj rho delta hi phi delta hj phi, and the integral is over rd and dx plus the twice epsilon summation over I from 1 to d delta hi phi, and then plus the n epsilon phi 0 square. This n epsilon is not the same as we add them, and sorry,
I1, maybe use the J1.
sorry,
You didn't say what is I1.
the I1.
Maybe it should be J1.
Oh, and then I started to rename. That's already okay. So the I1 was the J1, yes? Is that? And then to be nice, then please and correct. This is the J2. To have the same, just for psychologically, it's easier for me if I the same.
Because
These, and then here, thank you, J1, J2,
You need relative sign on the first column.
on the right hand side, what is the problem?
You need relative sign.
But told me the algebraic condition.
So here we have the 2, and what condition we have for this, that this quadratic form is bigger than, and I lost the minus, yes? That is why you are protesting. I didn't hear well, but I understood something is wrong. So with the minus, for this quadratic form, we have that it is bigger than or equal to the kappa, so that kappa times the sum of the squares which we have here. So that means less than or equal than minus 2 kappa times the sum of the squares of these integrated. So that means the sum of the L2 norms or squares of delta hi phi I from 1 to d plus then 2 epsilon and the same quantity So probably, okay, and here we got then, because we choose 2 epsilon to be kappa, and we got so take 2 epsilon to be kappa, and then we got the lemma, right? Okay, so probably it was very boring for those who are experienced with the variational approach already, because exactly the same kind of computation, not exactly the same, there is a slight difference, but on the formal level exactly the same computation. So we got the lemmas. So oops, sorry.
So you said before you gave the lemma with the m on the right hand side, and you had m be 0, so you still have to do.
Oh, that's right. Thank you. I nearly skipped the whole thing. There is still some work down. Right. Thank you, Eric, for this. So that was the m equals 0 only. I have been bored with. Okay, now the m equals greater than or equal to 1 situations. We want to do this recursively, so by induction on m. So to show the induction, I just consider m equals 1. So consider now the case m equals 1. Right. Then what we do, we so that means we have to so did I formulate it? Why should I want it? In fact, for me, I think the m equals 0 case is enough. Why? How was my formulation for the? Why have I written other than? Yes, there is no m involved. Sorry, something this lemma is enough to formulate for 0, so let me once again state and correct please if I have written something different. So the QE phi equals the 2 and phi LH phi plus the sum, and here 0, and the sum MH phi 0 squared rho from over rho 1 to d1, that this is less than or equal to the minus kappa and the sum delta hi phi square I from 1 to d plus n times the phi squared and 0. Wasn't that I used the m? So I want, please, the only thing I wanted to prove is this version. So if I made something, have written something different, that is lack of concentration. So this is what, and that means we prove the lemma. And then, still 10 minutes? About 10 minutes. Okay, and then now we prove the result. So we go the proof of theorem 2. And here, so they estimate to be, the only thing is the estimate to prove. And so the usual thing is to use Ito's formula for the square. So by Ito's formula, for the UH squared 0, so I consider now first m equals 0. Here I have the m. What kind of Ito's formula do I use here? So when m equals 0, then the UH is an L2 valued process which has such a stochastic differential, and everything here is L2 valued and satisfied. So this, what I'm using, is not those essentially more difficult Ito's formulas you have heard about already or learned about, but just a simple L2 valued, for L2 valued Ito processes, we use Ito's formula here. Again, I should say that the proof of the L2 valued version is for the square is exactly the same as you do it in finite dimension when you prove the Ito's formula for the square in finite dimension. Okay, so that means here we have that the DUH T squared 0 is summation over rho and MHUH, that is the rho here, plus the G rho square 0, right? So this, oops, I should write the dt first. Yes, this is the drift term in the Ito's formula for the square, plus twice UTH, and then MH rho UTH plus G rho T and DWT rho. I think I always make a mistake in Ito's formula still. That is so. I hope you agree. Yeah, that's all right. Okay, thank you. So we estimate this now. This is less than or equal. Then, when we write the UTH, LH, UTH, and here the square, we take the square and then the integral, then what we have is the Q, this is why we use that QT and UTH, yes, that part, plus, so then plus, then we have the UTH delta minus H beta F beta also twice. Okay, plus from here, what the other terms appear, that is plus twice the B, and we have as the, or why not to write just where the is the M. It is twice the MH rho UH G rho product plus the sum of G rho and square. So this is for the dt term, and plus the stochastic integral term. Now what letter to use for that stochastic integral? S, or maybe S, and then T, D, W, rho T for the stochastic integral term. And now the estimate of this. So you see that in the same way, but first we drop the delta onto U, and Cauchy-Bunyakovsky and again Young with the epsilon. Here Cauchy-Bunyakovsky, here there is also a derivative that immediately we use Cauchy-Bunyakovsky, and again with small epsilon, those terms where there is a delta, the difference, finite difference on UH, plus the G rho the L2 norm squared. So when we do this, and we take into account also our estimate for this QT, then we arrive to the following, that we have the minus kappa summation delta hi UH plus with a small epsilon, the similar term, but you understand in fact they will be opposite. H is up UH 0 ups, or I can write it like this, yes, as well, and then plus the N and the U H ups N times the U H squared. Okay, so that means we have this kappa half, and sorry, the dt should be written. The dt should be written plus the s t d w t term. Okay, so we here this I take then minus kappa half, and then get rid of this term. So we have then plus n UH squared 0 dt plus the st dwt.
F and G.
Sorry?
You need the term of F and G.
Yes, obviously I talked about and haven't written down, thank you very much, that one has also plus the ft and then the z plus the gt, and that's important, and then this dt plus the std dwt, and then the standard 1 minute. That first let us not, let us look at that. Let us write it in the integral form, put the minus to the other side, and then what we have is that ut h 0 squared plus the kappa half integral from 0 to t, this sum delta hi UH squared s ds is less than or equal than the u naught squared plus the integral from 0 to t fs 0 squared plus gs 0 squared ds plus the stochastic integral from 0 to t s dws. Now taking the expectation, we then get that expectation of this plus expectation of this is less than or equal than expectation of this altogether, and we kill this term by the usual technique that first we take the localizing sequence of stopping times. This is always a local martingale, so there is an increasing sequence tau n such that stopping with tau n, we have a martingale, then take the expectation, so everywhere first t minimum tau n is there, then we take the expectation, then this term is killed, then by Fathus lemma we go with n to infinity, and then we get the result for n equals 0. And sorry, I overstepped the time. Thank you for the attention. Then I hope